Today will be the first in a two-part series about determinants of order n. To get some intuition behind what this means, let's first review properties of determinants of order 2 and of order 3. Let's start with the definition of a determinant for a 2 by 2 matrix. Given a 2 by 2 matrix A, the quantity A11 times A22 minus A12 times A21 is called its determinant. Recall that one of the main properties is as follows. A 2 by 2 matrix is invertible if and only if its determinant is non-zero. There's also a geometric interpretation. Let's say that U and V are two vectors in the real plane R2, and let's let A be that 2 by 2 matrix having U and V as its columns. Then the parallelogram determined by these two vectors has area, absolute value of the determinant of A. In particular, the determinant of A is 0 if and only if its columns U and V are parallel. Finally, we have a nice identity that involves the determinant. We can consider the square of the quantities A11 times A12 plus A21 times A22 and the determinant to be equal to the products of the sums of squares. Let's put this in a slightly different way. When n is equal to 2, we have the following 2 by 2 matrix, and its determinant is again A11 times A22 minus A12 times A21. We can remember this using the following diagram. Let's take our 2 by 2 matrix A, and let's place in arrows by connecting the various diagonals. Here, we can place the arrows going from upper left to lower right, consisting of A11 and A22, to correspond to the product that you see in the determinant. However, the arrow going from the upper right to the lower left, consisting of A12 and A21, corresponds to the minus inside of the determinant. So in this case, when we place numbers along the arrows, we'll mean multiply these numbers together, and the orientation of the arrows either means we'll add the product or we'll subtract them. When n is equal to 3, we have the following matrix, and we can define the determinant as either the sum or the difference here for 6 terms. Recall that we mentioned that we can also write this determinant by using the diagram as you see. The idea here is that we actually have 5 columns. The first 3 columns are exactly the same columns in our 3 by 3 matrix A, but then we repeat the first 2 columns of A to round out the 5. Now we'll write in these 6 arrows, and we can look at how these 6 terms in the determinant correspond to this. We'll come back and we'll talk about this diagram a bit more later on in the lesson. But for now, let's try to move on to the general properties of determinants of order n. First, let's say that A is an n by n matrix. We'll define Aij with the tilde as that n minus 1 by n minus 1 matrix obtained from A by deleting row I and column j. Here are a couple of examples. When n is equal to 2, let's consider this 2 by 2 matrix. We'd now like to construct Aij tilde by crossing out row I, column j. For example, let's take a look at A11 tilde. Well, the element A11 without the tilde is just the element in row 1, column 1 of A. If we cross out the first row and cross out the first column, then we're simply left with the element A22. Let's move on to A12. Here we can take a look at the element in row 1, column 2. If we cross out row 1 and cross out column 2, we're left with the entry A21. Similarly, we can look at what happens when we have the element in row 2, column 1. If we cross out row 2 and cross out column 1, then we're left with the element A12. And finally, we can look at the element A22, and we could cross out perhaps row 2, column 2, and we'll be left with the element A11. Let's move on to a slightly more complicated matrix. Let's say n is equal to 3. Here now you can see that we have our 3 by 3 matrix, and we have various 2 by 2 matrices by crossing out the different rows and different columns. For example, in row 1, column 1, we have the element A11 for our matrix A. However, for A11 tilde, we need to cross out the first row and the first column, and now we're left with the remaining 2 by 2 matrix. This is the matrix that you see on your screen. And of course, we can move on, and we can do this for the various other entries that we have for our 3 by 3 matrix A. There are going to be a lot of matrices here to keep track of, but remember that the basic idea is that you take a look at the entry in the matrix A, you cross out that row, that column, and you're left with a smaller matrix. We'll use this now to write an inductive definition. We'll define the determinant of an n by n matrix A recursively as follows. When n is equal to 1, we'll just define the determinant to be the entry in the matrix, in this case, A11. However, if n is greater than or equal to 2, we'll define the determinant as a certain alternating sum. Let's take a look at what happens along the first row. Along the first row, we'll have entries in the form Aij, where of course j ranges between 1 and n. We can also cross out the elements in the first row and, let's say, column j to find the smaller matrix A1j tilde. We'll want to multiply by the determinant of this matrix. This is why we say that we're now defining things recursively. The following n by n matrix is called the cofactor of A. We'll define it entry by entry as follows. The ij entry of this cofactor matrix is a certain alternating sign times the determinant of the matrix Aij tilde. Remember that Aij tilde is what we get by looking at the matrix A and crossing out row I, column j. This matrix has entries which are determinants of smaller matrices. Finally, the n by n matrix known as the classical adjoint of A, some books call this the adjugate of A, is defined entry-wise as follows. Here, the ij entry is a certain alternating sign times the determinant of a ji tilde. Notice here how the subscripts are slightly flipped around. This is so that the cofactor matrix and the classical adjoint are transposes of each other. It'll be a little bit easier for us to keep track of the cofactor matrix, and at the end of the day, we'll just take the transpose in order to compute the classical adjoint. These are some rather strange definitions, but we'll spend time in today's lesson as well as the next lesson trying to explain why we've made these definitions. For now, let's just review an example. Let's say n is equal to 2. Well, if we like to compute the determinant, we need to take a look at what happens along the first row. Let's cross out perhaps the first row in the first column, or the first row in the second column, in order to compute the determinant. Here, we'd like to take a look at A11 and A12. Roughly speaking, the diagram here says what we would like to do is take a look at A11, and then we'll multiply by the remaining parts, in this case A22. Or we could take a look at A12 and multiply by the remaining parts. In this case, it's A21. We're going to now compute the alternating sum of these two in order to compute the determinant. That is, it's plus A11 times the determinant of A11 tilde minus A12 times the determinant of A12 tilde. If you recall, this was the recursive definition of our determinant. But looking at the diagram above, we see that this is the same as A11, A22 minus A12, A21. So our rather strange looking definition from the previous slide really is just the same definition that we've introduced all along. Now let's take a look at the cofactor matrix. Here, we're simply going to look at what is very similar to our matrix A, but we'll place in various changing signs, and we'll also place in the determinant for the smaller matrices. Remember that the matrix A consists of A11, A12, A21, and A22. With this now, we'll just place in plus or minuses and then take a look at the determinant of the corresponding Aij tilde. We'll see here that the cofactor matrix is computed as follows for a 2 by 2 matrix. This should look somewhat familiar. Remember that the classical adjoint is just the transpose of this matrix. And actually, we've seen before that the inverse of a matrix A we can compute in terms of the adjoint. It's just 1 over the determinant of A times this adjoint, namely the transpose of this cofactor matrix. Let's now take a look at n is equal to 3. In this case, if we'd like to compute the determinant, we need to write out the matrix A, take a look at the first row, and then start to cross out various columns. So you can see here, along the first row, we have A11, A12, and A13. We need to now cross out the remaining row and column to see what's left over. Roughly speaking, this diagram says that we'd like to take a look at A11 times the determinant of A11 tilde. This is just simply the determinant for the matrix A22, A23, A32, and A33. We can do the same for the other diagrams corresponding to A12 and A13. Now for the determinant, we need to take the alternating sum of these three. So we'll have a plus, minus, plus. In this case, we'll have an A11 times the determinant of A11 tilde minus A12 times the determinant of A12 tilde plus A13 times the determinant of A13 tilde. From this definition, we can now expand out the determinant for our smaller 2 by 2 matrices, and when we clear off the dust, we see that here we have a sum of 6 terms. Let's take a look at these 6 terms in a slightly different way. As in the previous lesson, we found that we can really express this formula by using the diagram that you have here on the screen. As a reminder, along the arrows, we want to multiply the terms together. So for example, A11 times A22 times A33 plus A12 times A23 times A31 plus A13 times A21 times A32 minus A12, A21, A33 minus A11, A23, A32 minus A13, A22, A31. Recall that the arrows just simply mean that we're going to multiply all of the numbers together that appear along the arrows, whereas the arrows going from the upper left to the lower right correspond to addition, and the arrows going from the upper right to the lower left correspond to subtraction. Next, we have the cofactor matrix. Remember that the cofactor matrix is what we find by looking at the determinants of the Aij tilde. Here you can see the expression that we have. Yes, in general, the cofactor matrix is a very long matrix to multiply out. We'll have these various alternating terms. You can see here the checkerboard pattern of the plus, minus, but we do have to compute determinants of smaller matrices. So in this case, to compute this 3 by 3 cofactor matrix, we'll need to compute various 2 by 2 determinants. Recall that the classical adjoint is just the transpose of this matrix. We won't worry about writing it out in detail here. However, what we're going to find later is that whenever the determinant of A is non-zero, the inverse is 1 over the determinant times the adjoint of this matrix. This is part of the reason we define the cofactor matrix and the classical adjoint. Thanks for watching.